Hi everyone. So we are now at topic 5. Topic 5 is known as thermochemistry. Now, the word thermal is pretty simple. It means heat. Okay? So what does heat have to do with chemistry? Well, pretty much everything. Okay? Heat is a form of energy. Okay? So a lot of people, when they say heat, what are they talking about? Are they talking about hot? Because that's what a lot of people would resemble heat as. Turn up the heat. Give me some hot air. Turn down the heat. Don't give me so much hot air. So, if heat is a form of energy, what is the true definition of heat? So let's take a look at 3 definitions that I have for you today. The first one, of course, is what I've been talking about for the last 10 seconds, heat. Okay? Mathematically, or in the realm of chemistry, the variable heat is given by the letter Q. Okay? And the definition of this is actually nothing more than a transfer of energy. That's right. It's a transfer of energy between objects. And these objects has different temperature within them. Now, the question is, what is temperature? Now, we'll talk about that in a sec. I'll give you the true definition of temperature. Temperature is actually a measurement of the kinetic energy that molecule is experiencing. In other words, how much they're vibrating. Because molecules or particles are always moving, right? They're always moving. If they're moving super duper duper fast, they're generating a lot of kinetic energy. As a result, the temperature will be high. If they're moving very, very slow, that means their kinetic energy is small, and so will their temperature. And heat, right here, Q, is representing a transfer of energy. So energy moving between objects, from one object to another. Okay? So from that on, let's kind of look at this in a sense of some physics right here. This is based, of course, on the second law of what we call thermodynamics. Now, you may be thinking, well, we're talking about the second law of thermodynamics. Have we ever talked about the first law of thermodynamics? Well, I guess kind of. We will get to it later on. But this deals, of course, with the second law of thermodynamics, where heat, will flow from high temperature to low temperature. Let's write that down. When will they stop transferring this energy we call heat? Well, it will stop until both object has the same temperature. Okay? And there's a word for that. This is called thermal equilibrium. So it's almost like saying, you have something really, really hot, and you're making contact with something not as hot. Coal, in fact. What happens? Well, the heat will transfer from the hot object to the colder object until both objects are at the same temperature. That's what we meant by thermal equilibrium. So that's what heat is. It's an energy. Pretty simple, huh? Let's take a look at the second definition that I want to kind of introduce you to, since this is really a start of a new unit. And this is a very important word. It's called enthalpy. Enthalpy, mathematically, is variable h. Okay? And what enthalpy is the amount of heat. The amount of heat an object has. Whoa. You mean you can calculate that? You can calculate the amount of heat content something have? Well, kind of, but it's actually very, very hard to do. The heat what does this say? The heat content. Of an object. You'll notice that I will stay away from saying stuff like object. I will say stuff like system. Very, very soon. When you have a chemical reaction happening inside a beaker, that is a system. So the chemical that is being reacting inside the beaker is a system. Around the beaker is known as the surroundings. So enthalpy, H, is the heat content or the amount of heat inside a system. Now I can tell you that right now. That's very, very hard to measure. That's very difficult to measure. So what are we doing with H? Well, we rarely use H. Very rarely will H be presented. What's usually presented is the change of heat content in a reaction from the reactant to the product. What is the change in the heat content? Rather than saying, oh, this chemical has this heat content, and what happened to this heat content after the reaction? No, nobody ever says that. Okay, most people talk about the change within the heat content. So let's do a little diagram right here. Okay, here's a beaker that I was just talking about. Okay, it's a solution. So what's happening in here, let's say, is a neutralization reaction. NaOHCl plus NaOH. This is what's happening inside this beaker. So what's happening in here is known as the system. Okay? Now, I can tell you this right now. So this is something that you'll find out very, very soon. Let me get my red. Okay? This reaction actually makes the solution hot. So what I meant by that is that it releases heat. So it releases heat. So what I'm illustrating right here with these arrows is heat being released by the system to what we call the surroundings. Okay, so outside the beaker, we say that, oh, this is the surrounding. This is what we are experiencing. You are part of the surrounding. So if you were to do this reaction right here in a beaker, and you put your hand near, these are your hands. I know it looks really weird looking. You'll notice that, oh, it feels warm. Now what that means is that the system is releasing heat to the surroundings. Okay? Now, do all reaction release heat? No, we'll talk about that very soon. Some reaction absorbs heat, so the arrow will go in the other way. Okay, why arrow goes in? Because it's pointing to the direction where higher temperature, you can say, will move towards the lower temperature. You can think of it that way. Or in this case, you can think about, hey, hotness is being released to the surrounding. That's why you feel hot. That's why if you have your hand near the speaker where the reaction is happening, you feel the heat. Feel like dancing already. Okay? So let's continue writing things down here. Of course, you, as a person who's doing the experiment, cannot measure enthalpy, okay, of a system. That's not something that you guys can do. You don't have the equipment at school to even closely perform that operation. But as I said before, you can definitely measure the change in enthalpy, because that's exactly what you're going to be doing quite a bit. Okay, and this change in enthalpy is represented by delta H, okay, with a final measurement, okay, subtracted to the initial measurement through a little device that we can build easily in a thing called colorimeter. And what we're going to be learning, of course, is colorimetry. All right? And this is very simple to build. All you need to do is get a couple of insulating material. The reason why you want insulating material is because you don't want heat to escape, okay? And you don't want heat to come in from the surrounding to disrupt what's going on in here. And a couple of thermometers. Maybe just one thermometer. Okay, and you're gonna watch how temperature will move. Okay, so if you were to build a colorimeter, okay, measuring what exactly is the delta H of this system right here, okay, you would turn the speaker into a styrofoam cup, maybe 2 styrofoam cup, okay, and put a lid on top and stick a thermometer in here. Okay, and what you're going to be doing, of course, is measuring the difference in temperature. Okay, so initial temperature, so before the reaction happens, and when the reaction is completed. Or you can say, by looking at the thermometer, what is the maximum, or in this case, minimum temperature that you're getting. Okay, and through certain mathematical formula, you will be able to find what delta H is. Okay, because there's no way you can find out what H is before and after. So you're really always looking at the difference in temperature, or in this case, the difference in the amount of enthalpy. So all in all, okay, let's kind of finish this off. So when delta H, which you're going to be measuring, is a negative number. Now, when will it be a negative number? It is a negative number when your final temperature is higher than your initial temperature. So this case right here with neutralization, that will give you delta H being negative. Because if this thing releases heat, you can pretty much bet that your thermometer will say, ooh, the temperature is going up. I can feel that too because this thing is getting hotter. Meaning that the final temperature will be higher than the initial temperature. This will in fact give you a delta H to be a negative number. We say that when delta H is negative, heat was released. Okay? This right here is an exothermic reaction where you feel hot. Pretty cool, huh? However, when delta H is a positive number. Now, when will that happen? That will happen when heat was actually absorbed by the system instead. So heat is not releasing to the surrounding. You're not feeling hot. In fact, heat is being absorbed by the system. Now, for this reaction, this event will not occur because this is an exothermic reaction. But there are certain reactions where it kind of absorbs the heat from the surrounding. You, as being part of the surrounding, will not experience hot, but you will actually experience cold because the system is sucking up all the heat. If you stick a thermometer in here, what you'll see is a decrease in temperature. The molecules are actually moving slower. This is known as an endothermic reaction, which will result in feeling cold. All right? So all of these, of course, are reactions that we're going to perform. We're going to do these testing to see different reaction or different chemicals being dissolved in water. Will they give off heat or will they make things cold? Okay? And usually when we do these experiments, we're doing it under a certain condition. So let's write that down. So when you are measuring, when you're measuring delta H, or you're performing some sort of experiment dealing with delta H, you're always doing it under what we call SATP condition. We call that a standard condition. SATP stands for Standard Atmospheric Temperature and Pressure. This is known as delta H naught. Okay? This little knot right here looks like a degree sign with a slash. Usually it has a slash. Let me just blow this up and draw a little slash right here. Usually it looks like this. This little circle with a slash is an indication that you're doing this experiment under 1 atmospheric pressure. Okay, which is really 100 kilopascal, depending on what type of units of pressure you are comfortable with, and at 25 degrees Celsius. Okay, so when you're doing your reaction or you're doing your experiment and you're doing it under this condition, we call that a standard condition. The whole idea here, of course, is that this is known as the standard enthalpy change of reaction. Why is that important? It's because these values are usually given in some sort of chemistry handbook known as the CRC handbook. Okay, the CRC handbook has information about pretty much every single reaction that there is out there. And somebody have already done these experiments for you. So somebody have already figured out this delta H for all types of reaction. But of course, they did it under standard condition, which means if the condition was changed, let's say, hey, you're not doing this experiment under 25 degrees Celsius, but you're doing this reaction at a very cold place. You're actually doing this reaction in the fridge or something, 4 degrees Celsius. Then this number is no longer the same number. You will have a different delta H if that's the case. Okay? However, we don't do our experiment in a fridge. We don't do our experiment outdoor. We do it in a regulated surroundings where the pressure in this lab is at 100 kilopascal and 25 degrees Celsius. We do our experiment under these conditions, and at these conditions, we say delta H is a naught. Delta H naught. And as I said, you want to know what is the delta H naught for this reaction? It's very simple. You just have to go to a CRC handbook or your IB constant booklet, and it will actually tell you what that number is. Hey, one of the things that we're going to do, hopefully we will do, is to prove that those numbers are right. Actually, those numbers are right. It's more like you're proving that you're right. And see how far you're off by looking at percent error. Hopefully you understand exactly what this introductory of delta H is all about. Okay, so let's kind of recap a little bit before I move on. Okay, so we first looked at heat being a transfer of energy that has different temperature. And what we do know is that heat moves from higher temperature to lower temperature until the two temperature equal, which we call thermal equilibrium. Then we looked at enthalpy, which is H, something that you really can't measure for a system. But what you can do is look at the change in enthalpy of a system using a method known as colorimetry. And of course, colorimetry is measured through a colorimeter, which is a couple of insulating material where the reaction will happen, and a thermometer that gauges the change in temperature. Okay, if delta H after you calculate it is negative, of course we call that exothermic. I think I spelled exothermic wrong right here. There should be an H. Okay, and by experiencing a exothermic reaction, it feels hot. Of course, when you have a decrease in temperature of the system, we can say that heat was absorbed, and that will be an endothermic reaction. And the experience of that is cold. If you're doing this experiment where you're finding delta H under standard condition, delta H is said to be delta H naught. Okay, and these are, of course, values where scientists have figured out by doing these colorimetry experiment. All right, so let's finish this off, okay, by looking at some charts, some graphs, and also by looking at my third definition, which is on temperature. Okay, so let's remove this. Okay, what did I do here? Oh, let me just do a new page. Just take a new page right there. Okay, and let's take a look at the third definition, known as temperature. Okay, what's going on with this? Oh, my goodness. Okay, I got it all straightened out. So, the third definition, which I kind of talked about already, is called temperature. And what that is really just a measurement of the average kinetic energy, which is the energy of motion, of the particles in a substance. Okay, so when you're measuring the temperature of something, you're actually measuring how fast these particles are moving. That's all it is. Okay, and what we're going to use is degrees Celsius. We're not no Americans. We're not going to use degree Fahrenheit. We know nothing about that. And since we're not talking about ideal situation, we're not going to be talking about Kelvin neither. So all our measurement, of course, in colorimetry is going to be based on degrees Celsius. Okay, and as a note, that for all of our experiment, okay, which means where we're going to be performing these experiments, which is really a classroom, we are working in what we call an open system. We are working in an open system. What does that mean? Is an open system? Well, very simple. Where matter, or both matter or energy, can move from system to surroundings. Okay? We've seen earlier that in a neutralization reaction, that heat energy is moving from the system to the surrounding. Okay? But in an open system, matter can also move from a system to a surrounding. You can even think of it as losing mass to the surrounding. And that happens all the time, right? Like, for example, if you're evaporating water, you're losing mass. Definitely. Because the water vapor, which is really water particle, is leaving your system and entering the surroundings. So when you weigh water after it cools down, you'll notice that it's lighter than before you heat it, because some of the matter has gone off to be part of your surroundings. That's what we're working with in a lab. Because we cannot be working in a closed system. That's crazy. Millikan Mills High School, what do you think we are? Okay? Because in a closed system, only energy can move. Can move between systems and surrounding. I think I need to be a little bit more clear here. Up here. Okay. I shouldn't say from system surrounding, but you know what? It's usually from system surrounding, so I'm just going to leave it. Okay. Now, there's also a scenario, which is this scenario, known as an isolated system. Now, this one we probably won't get to, okay? Which is, of course, no exchange. No exchange of energy or matter between system and surrounding. Now, you may be thinking, does that mean there's no reaction happening? I mean, that sounds like it. No, I don't mean by that. That's pretty good. Or else why would we talk about it? Okay? An isolated system is a lot bigger than you think. A lot bigger than you think. Then you have to take into account what we call the universe. The realm of our existence. Okay? The universe. There's a saying, energy cannot be created nor destroyed. It can only be changed from one form to another. And this changes, this creation, or non-destructible, whatever, cannot leave this universe. That's what this isolating system means. That, yeah, you did an experiment. You did a neutralization reaction. It released heat to the surrounding. But you're talking more than just your surrounding. You're talking about the universe. Is this heat gonna come out of the universe? I don't think so, Superman. Okay? This heat will stay in the surrounding and maybe used to drive other systems. Same idea. Can you just create the energy? Something outside of the universe and bring it to this universe? If you think so, you've been watching way too many sci-fi movies, man. So that's what this isolated system means, okay? Where there's no exchange of energy or matter, and you're not just talking about what's happening in your beaker, but you're talking about what's happening in this universe. Basically, that heat that you just released from doing the neutralization reaction is going to stay in this universe. It's going to be isolated. It's not going to go to another dimension, heating up another universe. I mean, that's pretty crazy to think about. I mean, if you are thinking about that, you must be crazy. I'm sure you guys think about that all the time. All right. Let's wrap this up. Okay. Let's clear this page out. Let's do a little bit of what I call like graph things out. And then we'll call it for the day. Okay, so in thermochemistry, which is really the introduction of what's going to happen in the next week or so, we use what we call an enthalpy level diagram. Biology uses this a lot too when it comes to cellular respiration. And what is it used for? It is used to illustrate thermal reactions. Okay? And you know that there's two types of thermal reaction already. There's an exothermic one and there's an endothermic one. So let's take a look at the exothermic one. An exothermic reaction. Okay, now what does an enthalpy level diagram look like? Well, it's really a graph where you have the y-axis indicating enthalpy, which is the amount of heat content of a system. And of course, you're graphing this against duration of the reaction in time. Okay? Remember, you can't really figure out what the actual number of an enthalpy is, but you can always start somewhere. So just say your enthalpy of your reactant is right here. This is how much enthalpy you started with. Right there, whatever that is. But what you do know is that at the end of this reaction, your enthalpy of products is down here. So what happened is that your reaction has gone through a decrease in enthalpy. This decrease in enthalpy is what experiences heat being released to the surroundings. As a result, delta H is said to be a negative number. Okay, so the amount of heat content of your reactant is higher than the amount of heat content after the reactant has become products. That's not surprising because what did I say exothermic feels like? That's right, it feels hot. Where did this hotness comes from? Definitely not Mr. Lung's face. It came from the reactants. So when the reactants break bonds and then form bonds to make products, heat from here got released out of the beaker and into the surrounding. That's why you feel hot. So we say that because you're losing heat, delta H is negative. And nature actually favors that, believe it or not. Nature actually favors exothermic reaction. Now, I have a couple of reactions here with a certain value that I got from the CRZ handbook, like this one. This is a combustion reaction, where you're combusting natural gas, methane. This is exactly what's happening in your furnace right now. And we will indicate the fact that this delta H is equal to 890 kilojoules of energy per every mole of methane that you're combusting. Note what I just said. Okay, this reaction right here releases 890 kilojoules for every mole of methane being combusted. So if I'm combusting 2 moles of methane, obviously this number will have to times 2. Where did I get this number from? Well, I got this number from a book, okay, where some dude already have done this experiment, and he did it when? Where? How? Well, a standard condition, of course, so I need to put a not here. And since this is a combustion reaction, I write C over here. So when you're going through these handbook and you're looking for the enthalpy change of the combustion of methane, you'll notice that they will give you this number per mole, along, of course, with standard condition telling you that, hey, I did this reaction at 25 degrees Celsius and 1 atmospheric pressure. And this is a combustion reaction, just in case you don't know. Duh. Okay. Now, what if I didn't do this under standard condition? Well, if you didn't do this under standard condition, obviously you can't put a not there. And this number is not going to be 890. It's going to be something else, depending if you're doing it at a higher temperature or lower temperature, a higher pressure or lower pressure. It all depends. Okay? Let me give you another one. I like to give you more. Let's do this one. We started with this, a neutralization reaction, which gives you water and a salt. As I said, this reaction releases heat. So in this case, it will be delta H. How much heat does this really release? Well, the book says, you always go by the book, 57.3 kilojoules per every mole. Now you may be thinking, mole of what? Well, it depends. Mole of whatever is limited. If this is limited, mole of NaOH. If this is limited, mole of HCl, depending on what's limited, because it's all about what's limited that drives the reaction in terms of how much, right? Again, this value is also based on standard condition, and this reaction is a neutralization reaction. Something that we were going to prove. Okay, this one we're not going to prove this one. This is dangerous, but we might prove this one. Okay, we might prove that one. All right, let's look at the other one. Okay, B. Let me use blue. People say the color blue represents coldness, so it's perfect to illustrate this to an endothermic reaction. So let's look at the diagram right here. Okay, again, it's enthalpy versus time, where if you have your reactants right here, and for some reason, of course, your product is all the way up there, what happened is that heat is being absorbed by the reactant, causing the products, of course, to be at a higher enthalpy state. It's almost like I grab some heat from the surrounding and look where I am right now, high up in the sky. So your enthalpy change is going to increase. This increase in enthalpy is where you see heat being absorbed by the system. In this case, delta H is going to be a positive number. All right. Hey, you won't be satisfied if I don't give you some examples of this, would you? So here's an example. This is actually a pretty cool example. Remember calcium carbonate? Man, we do a lot of things with calcium carbonate, do we? If we were to heat this up, oh yeah, if we would put this in a crucible and under a very hot flame, this will actually decompose to give you calcium oxide, and it will release some gas known as carbon dioxide. Okay, it's a decomposition reaction. This reaction is pretty cool. It's actually 180 kilojoules per mole worth of energy. Guess what? You're actually going to feel cold when this happens. When you're decomposing calcium carbonate, this actually will absorb heat energy from the surrounding, creating coldness. Okay? How do you think cold pack works? Don't you ever wonder? And hot packs, how do you think they work? It's like you have this baggie full of stuff, which you're probably asked not to open it up. When you need it, you sort of crack whatever's inside, shake it or whatever. What's happening inside those hot pack and cold pack is a reaction. For a hot pack, you're obviously doing some sort of exothermic reaction. For a cold pack, obviously you're doing some sort of endothermic reaction. That's what they are. All right, let me give you one more example. This is actually something that I might demo to you because I think it's cool. If I take some ammonium chloride, it's actually a very smelly substance, and I mix it with a base called barium hydroxide. If I were to mix the two, I will get barium chloride plus 2 ammonium hydroxide. Pretty smelly stuff. And the delta H naught for this, of course, is 162 kilojoules per mole. Now notice I did not indicate the reaction anymore. It's because I don't, you can if you want, you can put a D here if you'd like to indicate the fact that this is a decomposition reaction. Okay, you can put a double displacement here, but it really makes not much sense if they're not combustion or neutralization, which are quite specific if you think about it. Combustion is very specific. You're reacting with oxygen. Neutralization is very specific. It involves acid and base. These are so general that a lot of people just don't put the reaction type there because they're just too general. But they do show the fact that, oh, we did this as standard condition. So this reaction right here, okay, can absorb that much energy from the surrounding per every mole. All right, so you can pretty much bet that if I were to take, these two things and I would mix it in a beaker, I would mix it right here, and I would have a ruler right here. Let me put some water here. Okay, you'll notice if I do this reaction, this beaker will stick to this ruler because the water right here will turn to ice. That's how cold the reaction gets. Hopefully I have the opportunity later to demonstrate that for you. Maybe I'll just flip it to see that. See how cold it is? It won't fall off the ruler. Anyway, let's call it for today. And in the next class, let's do some calculations. Let's look at colorimetry in its entirety. All right, I'll see you later. Bye.